When you look up at the night sky, what do you see? You might spot a few familiar planets. Maybe Mars, the red planet, glowing faintly, or perhaps brilliant Venus, shining like a diamond. For thousands of years, humanity believed these were the only other worlds out there. Our solar system seemed to be a special, unique place. We had our small, rocky planets like Earth, and then we had the giant, gassy ones like Jupiter and Saturn. This was our neat little cosmic family. We thought we knew the basic recipe for how to build a solar system. But the universe, it turns out, is far more creative and surprising than we ever imagined. The last few decades have completely changed our view of the cosmos. Astronomers have turned their powerful telescopes to distant stars, and what they have found is truly mind-boggling. They have discovered thousands of planets orbiting other suns. These are called exoplanets. Suddenly, our solar system wasn't the only one, far from it. Let's take a trip to the chilly outer suburbs of our own solar system. Way out past the asteroid belt, beyond the mighty gas giants Jupiter and Saturn, you will find two lonely worlds. These are Uranus and Neptune. For a long time, we lumped them in with their larger neighbors. We called them all gas giants. It seemed to make sense. But this simple label hides a fascinating truth. Uranus and Neptune are not just smaller versions of Jupiter. They are a completely different kind of beast. Scientists now call them ice giants. The secret is in their composition. While gas giants like Jupiter are mostly made of hydrogen and helium, ice giants are different. The bulk of their mass comes from heavier elements we call ices. The discovery of thousands of exoplanets has been a game changer for astronomy. We are using incredible tools to find these distant worlds. One of the most successful methods is the transit method. Another powerful technique is the radial velocity method. As a planet orbits its star, its gravity makes the star wobble back and forth ever so slightly. We can detect this wobble by looking at the star's light. These methods have given us a catalogue of alien worlds, each one a new piece of the puzzle. When we do this, a surprising pattern begins to emerge from the data. We are finding an enormous number of planets that fall somewhere in between rocky worlds and gas giants. These planets have sizes and masses very similar to our own ice giants, Uranus and Neptune. This brings us to the central question of our journey. Think of it like a cosmic lineup of different characters, each with its own story. First up, we have the rocky planets. These are the small, dense worlds like our own Earth, Venus, Mars, and Mercury. They are made mostly of rock and metal, with a solid surface you could theoretically stand on. They form relatively close to their parent star, where it's too hot for cosmic ices to condense. Next in the lineup are the gas giants. These are the colossal rulers of the solar system. Think of Jupiter and Saturn in our own neighborhood. They are truly enormous, composed almost entirely of hydrogen and helium. Essentially, they are like stars that never quite gathered enough mass to ignite. Unlike rocky planets, they have no solid surface to speak of. They are vast, swirling balls of gas. For decades, scientists believed that planets came in these two main flavors, small and rocky, or huge and gassy. But the universe is rarely simple or tidy. Between the small, rocky worlds and the massive gas giants, there exists a third fascinating category. This is where our ice giants, Uranus and Neptune, reside. They are true middleweights of the planetary world. This in-between status points to a fundamentally different formation story and internal structure. The real difference between these planet types is not just what we see on the outside, but what they are made of on the inside. It all comes down to their core ingredients, the building blocks that were available when they were forming billions of years ago. Ice giants are a perfect hybrid. The vast majority of their mass is made of heavier elements, but these aren't the rocks and metals that define Earth. Instead, they're made of what astronomers call ices, volatile compounds like water, ammonia, and methane. Deep inside Uranus and Neptune, the immense pressure and high temperatures create a bizarre state of matter. The water, ammonia, and methane form a hot, dense fluid ocean or mantle that is thousands of kilometers deep. This unique internal structure generates their strange magnetic fields, which are tilted and offset from their centers. They are, in essence, giant worlds with a heart of exotic super-pressurized ice. The unique internal composition of ice giants directly shapes their outward appearance and extreme environments. Their famous blue hues are actually a direct consequence of their icy nature. The methane gas in their upper atmospheres absorbs red and orange wavelengths of sunlight. Beyond their beautiful colors, these worlds are home to some of the most extreme weather in the solar system. On Neptune, winds have been clocked at over 2,100 kilometers per hour, the fastest planetary winds ever recorded. Their magnetic fields are another feature that really sets them apart. Earth's magnetic field is neat and tidy, almost perfectly aligned with its rotational axis. The magnetic fields of Uranus and Neptune, however, are just plain weird. This combination of features gives us a clear profile for what an ice giant is. They're not just a point on a sliding scale between rock and gas. They are a distinct class of planet, born from a specific set of circumstances in the cold depths of space. To answer the grand question of what kind of planet is most common, we must first find them. This is no easy task. Planets, even giant ones, are incredibly faint compared to the blazing stars they orbit. Human ingenuity has found clever, indirect ways to unmask these hidden worlds. One of the earliest and most successful techniques is the radial velocity method. It's a cosmic dance of gravity, and we've learned to see the steps. Another powerful technique came to dominate the field: the transit method. If a planet's orbit happens to take it directly between its star and our line of sight here on Earth, it'll block a tiny fraction of the star's light as it passes in front. This method was revolutionized by space-based observatories, most famously NASA's Kepler Space Telescope. For 4 years, it stared unblinkingly at a single patch of sky containing over 150,000 stars. With the flood of data from Kepler and other surveys, astronomers could finally move beyond discovering individual worlds and begin to map the entire planetary population. They created a histogram showing how many planets were found at each different size range. The actual results were stunning. The most common planets were not the size of Earth, nor were they the size of Jupiter. Instead, the chart showed a massive peak for planets with sizes between that of Earth and Neptune. When they plotted a more detailed histogram of planet sizes, they saw something that wasn't just a single broad peak. Instead, it looked like two separate peaks, with a distinct valley, or gap in between. This feature is now known as the radius valley. One leading theory to explain this gap is called photoevaporation. The idea is that planets are born with a primordial atmosphere, but for planets orbiting close to their star, this atmosphere is under constant assault from high-energy radiation. The answer likely lies in the very process of planet formation itself. Imagine a young star, freshly born and surrounded by a vast, spinning disk of material. This is called a protoplanetary disk. In this spinning disk, tiny dust grains begin to stick together. Over millions of years, these clumps grow from microscopic grains to pebbles, then to boulders, and eventually to planetesimals, objects hundreds of kilometers across. The location within the disk is crucial. Close to the star, it's hot, and only rock and metal can solidify. Further out, beyond a point called the frost line, it's cold enough for water, ammonia, and methane to freeze into solid ice particles. A planet that forms just beyond the frost line has access to all that wonderful icy material. It can grow a substantial core much larger than Earth's. Instead of triggering runaway gas accretion, it gathers a modest atmosphere around its large, icy, rocky core. The existence of the Radius Valley and the abundance of mini-Neptunes points to a fascinating story about how planets are made. It suggests there might not be just one single recipe, but two main pathways that planets tend to follow. The first pathway leads to rocky worlds, planets that form in hot regions or are stripped of their atmospheres. The second pathway leads to ice giants, planets with larger icy cores that can retain significant atmospheres. But what about the gas giants like our Jupiter? They seem to be the product of a more extreme and perhaps rarer version of the second pathway. To become a gas giant, a planetary core needs to grow very large, very quickly. This theoretical framework paints a compelling picture. The most common planets in the galaxy are likely to be these in-between worlds. The mini-Neptune peak is so significant, it strongly supports the theory that ice giants are the galaxy's favorite type of planet to build. The growing evidence that ice giants are the most common type of planet is a truly profound shift in our cosmic perspective. For centuries, our view of the universe was shaped by what we could see in our own solar system. The Galactic Census tells a different story. It suggests that the most typical planetary systems out there might look very different from our own. Most stars are home to one or more of these Neptune-like worlds. This abundance has huge implications for how we understand planet formation. If the galaxy is churning out ice giants more than any other type of planet, it means the conditions required to make them must be very common. This forces us to re-examine our own cosmic backyard. If ice giants are the default, then why is our solar system so different? Our home might be the exception, not the rule. The discovery that mini-Neptunes are everywhere opens up a fascinating possibility. What if some of these worlds are not just smaller versions of Uranus, but something even more exotic? This whole idea has given rise to the water world or Hycean planet hypothesis. The idea describes a planet with a massive, globe-spanning liquid water ocean beneath a thick, hydrogen-rich atmosphere. Instead of a rocky surface with continents and seas, their surface would be the top of a planet-wide ocean, potentially hundreds of kilometers deep. Life, if it existed there, would be purely aquatic, thriving in the sunlit upper layers or around hydrothermal vents on the deep ocean floor. This concept dramatically expands our search for life beyond Earth. If Hycean planets are common, then the number of potentially habitable worlds in the galaxy could be far greater than we ever thought. They could be the most common type of habitable planet in the entire universe. The prevalence of ice giants fundamentally changes our ideas about how solar systems are built and evolve over time. The old model was pretty static, but planetary migration is a key part of the story. A Neptune-sized planet migrating inwards would act like a cosmic bulldozer, scattering smaller objects in its path. This could serve as a delivery mechanism, seeding young rocky planets with the ingredients needed for life. This forces us to consider planetary systems as interconnected ecosystems, not just isolated worlds. The fate of an Earth-like planet is intimately tied to the history of its larger siblings. We have to consider the dynamical habitability of a system, taking into account the influence of its most common and powerful residents, the ice giants. Their story is the story of the entire system. We began this journey by looking up at our familiar night sky. We saw our planetary neighbors as a simple family of small rocky worlds and colossal gas giants. But the discovery of thousands of exoplanets has shattered this simple model. The central question we explored was whether ice giants could be the most common type of planet in the galaxy. The evidence points towards a resounding yes. They're the true standard-issue planets of the Milky Way. We're standing on the shore of a new frontier, looking out at a sea of countless blue worlds. The James Webb Space Telescope is a key player in this quest, with the power to analyze the atmospheres of these common Neptune-like worlds. By looking at starlight that filters through their atmospheres, JWST can detect the chemical fingerprints of different molecules. This will give us our first real glimpse into the nature of these abundant planets. To truly understand this galactic population of ice giants, our quest must also turn homeward. Uranus and Neptune have suddenly become two of the most important celestial bodies for future exploration. For way too long, they've been neglected. Only one spacecraft, the valiant Voyager 2, has ever visited them, and its brief flybys more than 3 decades ago gave us just a fleeting glimpse. We actually have more detailed maps of Pluto than we do of these two full-fledged planets. A dedicated modern mission to one or both of our ice giants is no longer just a luxury, it's a scientific necessity. Just imagine a new robotic explorer, an orbiter specifically designed to study Uranus or Neptune. It could even deploy a probe to plunge into the clouds, directly measuring temperatures, pressures, and composition. Such a mission could finally solve the enduring mysteries that surround them. Our exploration of the ice giants brings us to a humbling and exhilarating conclusion. The universe is not only stranger than we imagine, it's actually stranger than we can imagine. Every time we build a new tool that lets us see a little farther or clearer, the cosmos surprises us. What other surprises await us as our technology continues to improve? Future telescopes will be able to probe the atmospheres of smaller and smaller planets. We may soon have the ability to analyze Earth-sized worlds for signs of oxygen, methane, and other gases that could hint at the presence of a living biosphere. The abundance of ice giants makes the universe seem a little less lonely. It suggests that the ingredients for life are distributed far and wide, incorporated into the fabric of the galaxy's most common planets. The surprising truth about ice giants is that their story is our story. It's the story of human curiosity, of our relentless drive to explore, to understand, and to see what lies over the next horizon. As we continue to gaze out into the great darkness, we do so with the knowledge that we live in a galaxy not of empty voids, but of endless possibilities. The most common worlds may be cold, blue, and distant, but they've shed a warm light on our understanding, forever changing our view of the universe and our place within it.